Hello, dear students. So, welcome to Wallah, and we'll continue from the last lecture. We have already completed the energy signals. Now we'll be completing the power signals and the other type of signals, that is even odd signals and conjugate symmetric, conjugate anti-symmetric signals. We'll be also completing systems and type of systems, that is what are systems, and the type of system, that is linear, non-linear, causal, non-causal, memoryless, static. Okay, all these kind of systems we'll be covering in this whole lecture. So let's continue, and we all know that from the last lecture that only two type of signals are power signals, that is periodic signal and the signals which are having constant amplitude for infinite duration, they are power signals. Okay, they are power signals. So let me write this thing. The power of any signal is defined by limit t tending to infinity, time tending to infinity. Okay, 1 upon capital T integration minus t by 2 to t by 2 mod of xt whole square dt. This is the formula of calculating power for any continuous time signal, but this is not for periodic signal. For periodic signal, the power is calculated by 1 upon t naught, where t naught is the time period. Okay, so power is 1 upon t naught, where t naught is the time period of the signal, minus t naught by 2 to t naught by 2 mod of xt whole square dt. Okay, this is the power of the periodic signal. In case of periodic signal, the 1 upon time period minus t naught by 2 to t naught by 2 mod of xt whole square dt is the power of the periodic signal, and this one is for the non-periodic signal. Remember that only two type of signals are periodic, so are power, that is periodic signal, and the signals which have a constant magnitude for infinite duration of time. Example ut, and other examples we will be doing here only. Okay, similarly for the discrete case, we have the power is equal to limit n tending to infinity, capital N tending to infinity, 1 upon 2n plus 1, n equal to minus n to capital N. Okay, xn whole square. Okay, this is the formula. This is the formula for calculating power of any signal, discrete signal. But in case of the periodic signal, the power is 1 upon time period n naught. Okay, and summation over a period, that is 0 to n naught minus 1 summation 0 to n naught minus 1 xn mod whole square. Okay, this is the formula for the periodic signals. Okay, so I hope you will remember these two formulas. These are two very important formulas for calculating the power of the signals. Okay, now let's move on. How to identify the power signals? There are two methods. To identify the power signals, as we all know. Only two type of signals are power signal: constant magnitude, let us say ut. Ut is power signal. Any signal which is DC signal, for example, any constant signal from minus infinity to infinity, that is A. It is a constant signal from minus infinity to infinity. This is also power signal. Third, another point is, for example, e to power j omega naught t. Now we know that e to power j omega naught t is a periodic signal. So this is a power signal. Fourth. Now suppose we have a signal, this is also very important point, fourth point. Suppose we have a signal that is sec of t, sec t. Now we know that sec t is 1 upon cos t, and obviously sec t will go to infinity, right? It goes to infinity. And since it is going to infinity, even if it is a power signal, okay, we always remember that there are three categories: neither energy nor power, power and energy, right? So first of all, if we draw sec t signal, sec t is 1 upon cos t, and when cos go to 0, sec t goes to infinity. And when sec t goes to infinity, thus it is neither energy nor power. Okay, sec t is neither energy nor power signal. Okay, sec t is neither energy nor power. Okay. So even if it is periodic, it is going to infinity, it will be neither energy nor power, because neither energy nor power is a signal which goes to infinity value at any time instant. So it is neither energy nor power. Any other signal? Sine omega naught t, it is power signal. Any other signal, triangular, periodic, any other signal, rectangular, periodic, it is always power signal. Okay. Now let us find out the power of the signal. Power of the signals. So let us take ut as an example. Okay. So power of ut will be using the formula limit t tending to infinity 1 upon capital T integration minus t by 2 to t by 2 ut square dt. Now since there is ut, so integration will be from 0 to something, right? This the integration will be 1 upon capital T 0 to capital T by 2 1 dt. Now if we integrate this, we will get the answer, that is t by 2 upon t, that is 1 by 2. Always remember that ut has power 1 by 2. ut has power 1 by 2. Okay. Now another example. Let us take any DC signal. Any DC signal. Let us take any DC signal. So the power will be 1 upon capital T. So sorry, limit t tending to infinity 1 upon capital T minus t by 2 to t by 2 a square dt. Now if we integrate this, we will get limit t tending to infinity 1 upon capital T a square into t. T to t will cancel and the answer will be a square. So remember that the power of the DC signal is simply square of that value. Okay. One very important point here is, that is, we know that we know about the orthogonal signals. Okay, orthogonal signals are those signals, that is, when we multiply the signals and we integrate them, we should get zero. That is the orthogonal signal. So always remember that sine, cos and e to power j omega t of different frequencies, if they are of different frequencies, then if they are of different frequencies, then they are orthogonal. Always remember that they are orthogonal. Okay, if they are of different frequencies. So for example, if we take an example, remember that a sine omega naught t is obviously a power signal because it is a periodic signal. The power is a square by 2. Similarly, a cos omega naught t, the power is a square by 2, and e to power j omega naught t, the power is equal to 1. Okay, so remember these results because they are very important, and many a times directly question is asked, we can easily solve them. Okay, one more example. Suppose we have this example, 2 sine omega naught t plus 5 cos omega 2t. So since the frequencies are not same, they are orthogonal to each other, and since they are orthogonal to each other, the power of the signal will be power of signal number 1 plus power of signal number 2, because they are orthogonal, and thus the power will be simply added. So the total power will be 3 square by 2 plus 5 square by 2, that is 25 plus 9 divided by 2. The answer will be 25 plus 9 is 34, divided by 2 is 17. Okay, this is the power. Okay, I hope all of you are able to do this. Great. But what to do? One more example for more clarity. What to do if the signal is this? Suppose the signal is 2 cos omega naught t plus 7 sin omega naught t. Now, since they are of same frequencies, they will not be orthogonal to each other. They will not be orthogonal to each other, and we will write it like this: 2 square plus 7 square cos omega naught t plus theta. You know that? You know this formula? Yes, I hope all of you are very much aware of this. That is a cos theta plus b sin theta is equal to under root of a square plus b square cos theta plus phi, and we know what is phi. Okay, we don't need it actually. We don't need what is theta. We don't need it. Okay, so we get this. So the power of this signal will be a square by 2, and what is a? A is equals to under root of this. So this will be so 7 square will be 49. 49 plus 4, 53 by 2. This is the answer. This is the power. Okay. So this is how we can solve it. I hope all of you are able to do it. There is no problem in these questions. Okay, we can easily solve it. Now, how the scaling and shifting affects the power? Scaling and shifting affects the power. For this explanation, first of all, let me take an example for more clarity. Let me take an example for more clarity. Suppose we have a periodic signal. Suppose we have periodic signal and it is a rectangular signal. Okay. Suppose this is a periodic signal and it is rectangular. 0, T naught, T naught by 2, T naught by 2 with a minus sign. Okay. Now, this location is T naught by 4 and this location is minus T naught by 4 and height is A. This is your signal xt. Let us assume that, and it is periodic signal. So how to find out the power of periodic signal? We know that power of the periodic signal is equal to 1 upon time period, that is T naught, 1 upon time period, that is T naught here, integration over a time period, that is minus T naught by 2 to T naught by 2 xt ka whole square dt. Okay, this is 1 upon T naught. Xt means xt is a from minus T naught by 4 to T naught by 4, otherwise it is 0. Otherwise it is 0. A square. So this will calculate, this will come out to be a square T naught by 2 divided by T naught, and thus it will come out to be a square by 2. This is the power. Okay. Now assume that we shift it. We shift the signal. We do the shifting of the signal, and obviously shifting does not affect the amplitude. Shifting will not affect the time period. So power will not be affected by the shifting. That is very clear to all of you. Okay. So shifting does not affect the power. That is very much clear. First point. Second point is, now what happens when we do the scaling? So let us take the same example and do the scaling. Scaling means let us compress the signal by factor of 2. Let us compress the signal by factor 2. So if we compress the signal the time period will become T naught by 2 and everything will get contracted. This will become T naught by 4, this location will become T naught by 8, this will become minus T naught by 8, T naught by 4, minus, and so on. Same rectangle will be at T naught by 4, sorry, T naught by 2, okay, and again it will repeat. Height will not change by scaling, okay. So this is the signal, we scaled it, and thus now the period is T naught by 2. Now the power will be 1 upon time period, that is T naught by 2, and over one period minus T naught by 4 to T naught by 4, the signal is amplitude A from minus T naught by 8 to T naught by 8 only. So if we integrate this, we will get that the power remains the same, A square by 2. Power remains the same. So power is not affected by scaling also. Time scaling does not affect the power. Okay, time scaling does not affect the power. So let us write the conclusion. Now conclusion is very important and you should remember this conclusion. Time scaling do not affect the power. Okay. Time shifting does not affect the power. Time shifting does not affect the power. This is second point. And third point is, but if we multiply any signal, suppose xt has power p, if we multiply it by capital A, then the power will become A square times the original value. Okay, A square times the original value, because when you multiply any signal, then obviously the power will get multiplied by the square of that value. Okay, now let us practice this here in this question. Shifting does not affect the power, first point. Scaling does not affect the power, second point. And third point is, when we multiply any signal by a constant, then power gets multiplied by a constant square. Okay, so if xt is having power 24, then xt plus 10 will have power 24. Scaling does not affect the power. Okay, scaling does not, the answer will be 24. Okay, x of 2t minus 10, scaling and shifting does not affect the power, 24 only. We have multiplied the signal by 5, so the power will get multiplied by 5 square, that is 24 into 25. This is the answer. And last is, scaling and shifting does not affect the power, but this 10 multiplication factor will affect it. So we'll get 24 multiplied by 10 square, 2400. Okay, this is the result. These are the results that we have got. Okay, or I think all of you have understood this. Great. Now, so we know that any signal which will touch infinity at any particular time instant will be neither energy nor power. That's a very simple and basic definition of neither energy nor power. Okay, we know it. No need to write it here. Now, let us find out the answers of some questions. Let us solve some questions. Okay, so this red signal, we are very much familiar with this red signal, all of you. This red signal is 5 rect t by 20. So this is the signal from minus 10 to 10. Okay, from minus 10 to 10, height is 5. Okay, so now we can easily see the result. That is, we know the energy of this signal, that is height square multiplied by width, that is 25 into 20, that is 500. I hope all of you are able to do this. Great. Next, this signal. This is a signal which will have a width of minus 50 to 50. Height is 4. Height is 4 minus 50 to 50. So the energy will be height square multiplied by width. That is 1600. Okay. I think you are able to do it. Great. So just tell me, this is energy signal or power signal? Since it's a finite duration signal, amplitude is also finite. So this is energy signal, no doubt about it. High energy, the amplitude is finite and it's a finite duration energy signal. This is a signal which is of decaying in nature, starts from 1.0. It is of infinite duration, but it is decaying in nature. So this is energy signal. This is energy signal. I hope all of you are able to do it. This is a signal 1 upon T ut. 1 upon T ut. 1 upon T means at T equal to 0, it will touch infinity. At T equal to 0, it will touch infinity. It will touch infinity value. And since it is touching infinity, what is the signal? It is neither energy nor power. Great. Next. Okay, one more very important point for energy and power signals, that is this. Okay. One more very important point left for energy and power signal is that yes, just a moment. Let me make a dry chart for it. Any signal, if it is energy signal, then its energy is finite. Energy is finite and power is 0. Always remember that. If we know that it's an energy signal, then energy will be finite, but power will be 0. Okay, if it is power signal, then power will be finite and energy will be infinite in this case. And third is neither energy nor power signals. Their energy is also infinity and power is also infinity. Just remember this values. They can ask you in MSQ or match the following type of problems directly. Otherwise, for us now it is very easy to identify that it is a power signal, energy signal, or none of these. Okay, great. Now let's move on to the even and odd signals. Okay, this actually is not very important, but many a times in continuous time Fourier series and Laplace, these things are very important. What is an even signal, what is odd signal? That's why we are going to study it here. So even and odd signal. Even signals are those symmetric about the y-axis or the amplitude axis. Okay, it is symmetric about the y-axis or amplitude axis. Always remember that it is symmetric about the y-axis or amplitude axis. So it is written like this: xt is equals to x of minus t. Okay, symmetric about the y-axis. Okay, we'll see figures for this. Or it is x of n is equals to x of minus n. So both are correct. Okay. The odd signals, are, they are anti-symmetric. They are anti-symmetric about the y-axis. And what is the definition? The definition is x of t equals to minus times of x of minus t, or x of n equals to minus times of x of minus n. So these two are the equations that they follow. So let us see a figure for more clarity. So suppose we have a signal. So we can see that this is the value 5.0, let us say minus 10 and 10. So can we see that this signal is symmetric about the y-axis? Both sides it is same. Both sides it is same, symmetric mirror image. Okay. So it is a even signal, right? This is the even signal. This is an even signal. Okay. Similarly, we have anti-symmetric signals. Suppose this is a signal. At 0, there is a discontinuity. At 0, there is a discontinuity. Okay. So we can see that minus 5 and height is minus 10. Let us say this is 10 and this is 5. Okay. Now we can see that this is anti-symmetric. Anti-symmetric now. We can see they are opposite to each other. Anti-symmetric, opposite to each other. So this is odd signal. Odd signal. Okay. One more thing about odd signal is one more figure for more clarity. We can see that this is also odd signal. Okay. This is also odd. So this is also odd signal. We can see that this is also odd. It is anti-symmetric about the y-axis. Is it correct? Is it clear to all of you? This is also odd signal. So let us do the marking. Minus 5, 5, height is 5, height is minus. Okay. So we can see that this is also anti-symmetric, right? Okay. So these are odd signals. One more thing about odd signal, bulky two more properties about odd signal. Let me check if there is a, yes, there is a page for it. So now let's move on to a few points. Always remember that even signal multiplied by even signal is equals to even signal. Okay, even signal multiplied by even signal is even signal. Even signal multiplied by odd signal is odd signal. Similarly, odd signal multiplied by even signal is equal to even signal. Oh, sorry, odd signal. And last is odd multiplied by odd is even. Okay, so these are the properties that we can use. Similarly, even divided by even is even. Even divided by odd is odd. Odd divided by even is odd, and odd divided by odd is. So these kind of properties we can use many a times. Okay, great. Now properties of even and odd signal. There are two basic, very simple properties that we should also remember whenever we are solving the signal system questions. So properties of even and odd signals. What are the properties? There are two properties. For the odd signal, let us say odd signal is more important here. Odd signal, we know that it is anti-symmetric. So minus infinity to infinity, odd signal integration. Odd signal integration is 0, right? Minus infinity to infinity, odd signal integration is 0 because we know that it is anti-symmetric. So one region will give positive, one region will give negative, and they both will cancel each other. Okay. Second is, since odd signal xt is equals to minus times of x of minus t, or xn is minus times of x of minus n. So we can see that at t equal to 0, this will be x0 is equals to minus times of x0. So we can see that x0 will be 0. That is at t equals to 0, the signal should have value equal to 0. At t equals to 0, odd signal must have value equal to 0. At t equal to 0 or at n equal to 0, the value of the signal has to be 0. But we can see that this property is not valid here. Can you see that? The property is valid here also, because at t equal to 0, there is a discontinuity, right? At t equal to 0, there is a discontinuity. At t equal to 0, there is a discontinuity, right? So, what Gibbs says about discontinuity? The value of the signal at discontinuous point. Gibbs says that the value of the signal at discontinuous point is value of the preceding value, that is minus 10, and the value next to it, that is plus 10. So take the average of it, minus 10 and plus 10, take the average of it, the average will be 0. That is the value of the signal at the discontinuity point. So according to Gibbs, the value of the signal here is 0 only. Okay, so don't get confused about it. This property is 100% correct and valid everywhere. For odd signals, at t equals to 0 or at n equals to 0, the signal is having the value equal to 0, right? Next property for the even signals. Since the signals are symmetric about the amplitude axis, okay? So, if we are integrating from minus infinity to infinity, any even signal, that will be equal to 2 times of 0 to infinity even signal integration. Okay, even signal 0 to infinity 2 times. Okay, so this is a property, but it is not very much useful. This property is very useful, and this property will give us one very important result, that is this. I am writing it here itself. There is a space available. So, as we know that even signal multiplied by odd signal is equals to odd signal. Okay, we have seen this property in the last slide. Even signal multiplied by odd signal is odd signal. So if we integrate minus infinity to infinity even signal multiplied by odd signal dt, this will give us a 0. Okay, if we have any even signal and if we have any odd signal, we multiply them and we integrate them from minus infinity to infinity, then we will get result 0. Why? Because even into odd is a odd signal, and odd signal integration from minus infinity to infinity is a 0. So we can see that even and odd signals are always orthogonal to each other. Okay, great. From here we have one more property that is very, very important, and many a times the question is asked on this property. Thus, if we have any signal xt, that is a sum of even signal and odd signal. Okay, if we have any signal xt, that is a sum of even signal and odd signal. Now the even signal and odd signal are orthogonal to each other. So we can see that energy of x will be equals to the energy of the even signal, plus energy of the odd signal. Okay, because we know that when the signals are orthogonal, this property is valid. So this property is valid here. Now, this is also a very important part, that is any signal, any random signal xt or xn can be broken or can be written into its even part and odd part. Okay, or we can say that any signal xt can have a even part and odd part. So we should know the formula for it, that is even and odd part of a signal even and odd part of a signal. So suppose xt is a signal, we can write it like this: xt plus x of minus t plus xt minus x of minus t, and we divide it by 2. Yes, we can write it like this because this term and this term will cancel each other and we will get 2xt divided by 2, that is xt only. Okay. So we can see that xt is equal to xt plus x of minus t divided by 2 plus xt minus x of minus t divided by 2. So we can see that this is the even part. Okay, always remember that this is the even part of the xt and this is the odd part of the xt. Remember this formula. They can ask you any question directly. This is the even part of xt, even part of xt, and this is the odd part of xt. Odd part of xt. Okay, so this is for the continuous time domain. Similarly, we can have for the discrete time domain also. Okay, xt is written as even part plus odd part. What is even part? Even part is xt plus x of minus t divided by 2. xt minus x of minus t divided by 2 is the odd part. Okay. Similarly, for the discrete also, we have xn can be written as xn plus x of minus n divided by 2 plus xn minus x of minus n divided by 2. Okay, this is the even part and this is the odd part. This is the even part and odd part of the signal. I hope all of you are able to do it. Right. Great. So remember these formulas. These are very, very important. These are very, very important. Okay. I'm just writing the conclusion here. The conclusion is any signal xt can be written as a sum of even part and odd part. Similarly, any signal xn can be written as the even part and odd part. Okay. Great. Now, this property, this thing is the energy of the even part and odd part. The concept is that since xt can be written as the sum of even part and odd part, and just now I have told you that these two are orthogonal to each other because even signal and odd signal are orthogonal to each other. Okay, so we can say that energy of the signal x is equals to energy of the even part plus energy of the odd part. Energy of the signal ex is equal to energy of the even part plus energy of the odd part. Okay. Great. So this was the formula that actually I wanted to tell you. So even signal and odd signal are orthogonal to each other. Second thing, odd signal has 0 value at n equal to 0 at t equal to 0. Third thing, any signal can be written as sum of even part and odd part. Last, energy of the signal is equals to energy of the even part plus energy of the odd part. Okay, these are the properties that we have seen. Now next is conjugate symmetric and conjugate antisymmetric. These properties are important because these are useful in Fourier transform, Fourier series and Laplace transform. Okay, these properties are useful there. So let us see the properties of conjugate symmetric and conjugate antisymmetric. What are these? Okay, so first of all, let us see the basic definition. What is the basic definition of this? If xt is any complex number, any complex signal, sorry, since we are talking about conjugate, so we will be taking complex signals in consideration. Okay, we'll be taking complex signals in consideration. So, conjugate symmetric. Conjugate symmetric, a signal is called conjugate symmetric. When it is conjugate symmetric, the definition is exactly similar to the even one. Even, what was the property or definition for even? For it was xt is equals to x of minus t. Here for conjugate symmetric, the property or the equation is same as that of even. The only thing is we put a conjugate here. So this is the condition for conjugate symmetric. Xt is equals to x of minus t conjugate. Okay, next. A signal is conjugate antisymmetric. When it is conjugate antisymmetric, the property or the condition is exactly same as that of odd. Okay, that is x of t is equals to minus times of x of minus t. Just put a conjugate here. So this is conjugate symmetric, this is conjugate antisymmetric. Okay. Now let's see the condition for conjugate symmetric signals. There are few properties which are very important, and directly they can ask you a MSQ on these properties. So, conjugate symmetric signals. So if xt is a complex signal, it has some real part and some imaginary part. Okay, it has some real part and imaginary part. This is the real part. This is the imaginary part. Okay, this is the imaginary part. So, since it is conjugate symmetric, since the signal is conjugate symmetric, signal, so it will follow the property of conjugate symmetric. What is the property of conjugate symmetric? The property of conjugate symmetric is xt is equals to x of minus t whole conjugate. That is same as that of even one. Xt is equals to x of minus t, only there is a conjugate sign here. So we can say that at plus jbt is equal to a minus t plus j b minus t conjugate. Okay, we put a conjugate here. Now we'll first of all solve the conjugate sign. The conjugate sign is a of minus t minus j b of minus t. Now we will equate the real and the imaginary part of RHS and LHS. We'll equate the RHS and LHS equation, real and imaginary part. So AT is equals to A of minus T, and we can see that BT is equals to minus of B of minus T, because here we have a minus sign with the imaginary part. Okay. So from here we can see that if the signal is, this is conclusion, just remember this, if the signal is conjugate symmetric, then the real part of the signal is even and imaginary part is odd. If signal is conjugate symmetric, then real part is even. Yeah, we can see that real part is even, but imaginary part is odd. Okay, imaginary part is odd. Great. So I hope all of you are able to recall this. This is a very important condition and that you should remember. Second is conjugate symmetric properties only. Suppose we have a number xat plus jbt. Okay. Now how to find out the magnitude of a complex number? Magnitude of a complex number is given by magnitude of the complex number, magnitude t is equals to under root of at square plus bt square. Okay, under root of real part square plus imaginary part square. So this is the magnitude of the conjugate symmetric signal. Now if we put minus t here, m of minus t will be equal to under root a of minus t whole square b of minus t whole square. Okay. Now a of minus t plus b of minus t whole square. So a of minus t is equals to at, as we know that, and b of minus t is minus bt whole square. So this minus sign will go because of the square term. So we can see that this will come out to be under root of at square plus bt square. So we can see that m of minus t is equal to mt. M of minus t is equal to mt. Okay, m of minus t is equal to mt. So we can see that the magnitude of magnitude is even. Can you see this? Magnitude is even. Magnitude is even. Okay. But what about phase? The phase phi t is equal to tan inverse the imaginary part and the real part. Okay. Bt upon at. Now phi of minus t is equal to tan inverse b of minus t upon a of minus t. Now b of minus t is minus bt upon at. A of minus t is at. Means the denominator is not changing, the real part is not changing, only the imaginary part is getting negative. Okay, we can see that b of minus t is minus bt, right? And a of minus t is at. So this will give you minus times of phi t. Phi of minus t is equals to minus times of phi t. So we can see that the phase is odd. Phase is odd. Okay. Sir, how we got this result? So for that, I have an example for you. So before moving ahead, I have one more example for showing this term. Okay. So let us take an example. Suppose we have 3 plus 5j a number. Okay. So where it will be present? It will be present in the first quadrant. Great. 3 is a real part, 5 is the imaginary part. This will be present in the first quadrant. Okay, this will be present in the first quadrant. So this is your theta angle, that is tan inverse imaginary part upon real part. Okay, tan inverse 5 by 3. Now we have to find out if this is tan inverse 5 by 3, where we will get. Okay, we want this na, tan inverse minus 5 by 3 location. We have to find out tan inverse minus 5 by 3 location. So we have to find out tan inverse minus 5 by 3. So tan inverse minus 5 by 3 means the imaginary part is minus 5 and the real part is 3. Imaginary part is minus 5 and the real part is 3. So this value or this signal or this point where the imaginary part will be minus 5 and real part is 3, it will go in fourth quadrant. Minus 5 and theta. Okay. So we can see that this will go in fourth quadrant. So this angle will be minus theta. Okay. Just let me tell you one more thing, one more time. If this phi t is tan inverse b by t, phi of minus t is coming out to be tan inverse minus bt by at. That is, if we have tan inverse 5 by 3 as the initial angle, now the angle is tan inverse minus 5 by 3. That is, imaginary part is getting negative. So since imaginary part is getting negative, the point will move from first quadrant to fourth quadrant, and this the angle. If the initial angle is phi, then the new angle will be minus phi. Okay. So that's why the angle is odd here. Okay. So we can see that the real part of conjugate symmetric is even. Imaginary part is odd. Magnitude plot is even. And phase plot is odd. These are the 4 things that you should always remember about the conjugate symmetric signals. I hope all of you are able to do it. Now let's talk about the exactly similar analysis for conjugate anti-symmetric signals. Exactly similar analysis. So let us take xt is equals to at plus jbt. Okay. Now conjugate anti-symmetric means the property is same as odd, only there is a conjugate sign here. So we'll put it. So we have at plus jbt is equal to minus times of a of minus t plus jbt conjugate. Now we'll put a conjugate, we'll take conjugate inside. So at plus jbt is equals to minus a minus t, and conjugate will convert this plus sign into negative, and negative will make it finally positive. And now then we will equate the real and the imaginary part. So we can see that at is minus a of minus t and bt is equal to b of minus t. So we can see that in case of conjugate anti-symmetric, the real part is odd. Can you see that? Real part is odd and imaginary part is even. Imaginary part is even. I hope all of you are able to do this. Great. Now for conjugate anti-symmetric signals, we have for magnitude, so xt is equals to at plus jbt. So now let us find out the magnitude. At square plus bt square. Great. Now m of minus t. So we put minus t in the whole equation. A of minus t whole square, b of minus t whole square. Now from the previous analysis, we know that a of minus t is minus at. And bt and b minus t are equal. So square will remove this minus sign. So this will come out to be at square plus bt square. So we can see that m of minus t is same as mt. M of minus t is same as mt. So we can see that the magnitude is even here also. We can see that the magnitude is even. Now let's talk about the phase. Now let's talk about phase. Phase is tan inverse bt upon at. Okay. Now phi of minus t will be tan inverse b of minus t divided by a of minus t. Now here, if we put the condition b of minus t is equal to bt and a of minus t is equals to minus at. So here we can see that the real part is getting negative. So just come back to this slide. Real part is getting negative. So this term will go here. What is the meaning of this? So since the real part is getting negative, tan inverse 5 by minus 3. Real part is getting negative. So this dot will go to second quadrant. And now the angle, this has no relationship with theta. Means relationship is not even and neither even nor odd. Rather, this angle will be pi minus theta. Okay. So we can see that the phase term will be neither even nor odd, because this will not have any relationship with the previous angle, this angle. Okay. Okay, rather this angle will be pi minus the previous angle, So phase is neither even nor odd. neither even nor odd. Okay, so we can just quickly write for the conjugate anti-symmetric signal, real part is odd, imaginary part is even, magnitude part is even, and phase is neither even nor odd, neither even nor odd. Now conjugate symmetric and conjugate anti-symmetric part of the signal. As we have the even and odd part, similarly we have conjugate symmetric and conjugate anti-symmetric part for any signal. What are these? Exactly similar way. So xt is equals to this was the even part and this was the odd part. You all remember the formula? Yes. Simply put, conjugate here, it will convert into conjugate symmetric part and conjugate anti-symmetric part. Okay, exactly similar for the discrete also. This was the even part, this was the odd part. Simply put, conjugate here, this will become conjugate symmetric, this will become conjugate anti-symmetric. So this is how you can remember these all things. Okay, you can remember these all things. Okay, so now let's move on to the systems and type of system. Okay, so let's continue. So now let's start the understanding of the systems and type of systems. Okay, what is a system? So we assume that system is a black box that converts one signal into a desired signal. Okay, that actually do the computations on the input signal, and from that we get the desired signal. From that we get the desired signal. That is the system. Okay, so system is a black box. We don't need to know what is inside the system. We only need to know what is actually it is doing. So system is a black box that convert the input signal into desired signal. Okay. There are many type of systems. The questions asked in the GATE exam is of the format that the input-output relationship. The input-output relationship is given to us. The input-output relationship is given to us. Okay. The equation relating the input and output is given to us in the question, and we have to find out the type of system. Okay, this is the pattern of question that are asked in GATE exam. What are the type of systems we have? Memoryless and memory system, or static dynamic. Okay, remember that memoryless system is also called static and memory system is called dynamic. Second is causal, non-causal. Third is linear, non-linear. Fourth is time variant, time invariant. Fifth is stable, unstable, and sixth is invertible, non-invertible. Okay, so we'll be looking at all these six type of systems. We'll be looking at how to find out the type of system. Okay, now first of all is a memory and memoryless system. Memory and memoryless system. So first of all, let me tell you what is the definition. Memoryless system means memoryless system means memoryless system means that the present output is dependent only on the present input. Okay. So memoryless system means that the present output is dependent only on the present input. Okay. This is also called a static system. This is also called static system. Okay. Now, what is memory system? So, if the present output depend on any other value, of input, any value, if the present output depend on any value of input, other than the present input, any value of input other than the present input, other than the present input, the system is memory system. And it is also called dynamic system. It is also called dynamic system. Now, it is very important to see the method how to check it. Okay, this is the definition. What is the definition? If at any particular time instant, if in any system the present output is dependent only on present input, then it is memory system, memoryless system. Otherwise, if the present output is dependent on any value other than the present input, then it is memory system or dynamic system. How to check? What is the method? The method is very simple steps. Step number 1. So, what is the type of question? The type of question is we have the input output relationship. We have the input output relationship. Okay, we have the input output relationship, and we have to find out the type of system. Input output relationship means we have the relationship between yt and xt. We have the relationship between yn and xn. Okay, we have these relationships. So step number 1 is find the output for t equals to -2, -1, 0, 1 and 2. For these time instants, simply find out the output. Okay, simply find out the output. Step 2, if for any time instant okay, yeah, we have find out the output for -2, -1, 0, 1 and 2. If for any time instant the output depends on input other than the present input, then the system is memory system. Then the system is memory system. else it is memoryless. Else memoryless. Okay, let me see, else it is. Let us do one example for this. Let us do one example on this. Okay. Okay. Just a moment. Okay. So let's try these two questions. What are the questions? Yt is equals to xt plus sine of t plus 4. What is the shortcut for checking the memoryless or memory system? What is the shortcut? Let me tell you the shortcut also. The shortcut is, or the jugaad is, if the variable, inside, or if the variable in y and x is same, then the system is memoryless. Okay? Else not. This is the shortcut, that if the variable inside the y and t are same, then the system is memoryless. Otherwise, it is memory system. Okay. So let us see that here. The the variables are same. Yes, yt and xt variables are same, and this is not affecting the type of system because this is not the input. So this will not be taken into consideration while we are finding the type of system. Only these are effective. These are important. This is not important. This will be cancelled for while doing the analysis. So we can see that, we can also see that y0 is equals to x0 plus sine 4. So we can see that the present output is dependent on present input only. Okay, y1, the present output is dependent on present input only. So if the variables are same, then it is memoryless system, memoryless. So this is memoryless. Okay, now this one, x of t plus 4. So we can see that the variables are different. Here we have t, here we have t plus 4. So gone. So this is memory system, memory. This is memory system. Also we can see that y0 is equals to sine of x of 4. We can see that y0 is dependent on x4. So it is dependent on the future value of input, not the present value of input. Okay. So this is the system which is memory system. Okay. I hope this is clear to all of you. Great. I hope all of you are able to do it. Great. Let's move on. Let's do one more example. Yt is equals to x mod t. Okay. So here also we can see that Here also we can see that the variables are different. So it is memory system. I hope you are able to do it. Next. This example. Here also we can see that the variables are different. Okay. I think all of you are able to do it. Here also the variables are different. This is t square 2t. So here the variables are different. This is 2t and this is t square. So it is memory system. Great. Next. Here also we can see that variable is t. Here is variable is cos t. Variable is cos t. So this is also memory system. So the shortcut is always valid. The shortcut is always valid. We need not worry that when it is valid, when it is invalid. It is always valid. It is always valid. Okay. Now let's move on to the second one, that is causal, non-causal and anti-causal. What is the definition of causal, non-causal and anti-causal? In case of anti-causal system, the present output is dependent only on the future inputs. The present output is dependent only on the future input. Present output depends only on the future input. ठीक है ना? The present output depend only on the future input. Okay. In case of causal systems, the present output does not depend on future input. This means that in case of causal system, it can depend on past or present inputs. Okay, so it can depend on past or present inputs. Can depend on past or present inputs, right? Great. Okay, so anti-causal means present output is dependent only on future inputs. Second, causal, it will not depend on future, rather it will depend on past or present. And third is non-causal. Any system not satisfying these two conditions is non-causal. Any system not satisfying the above two conditions any system not satisfying the above two conditions is non-causal. Okay. Now, how to check? The checking method is almost similar to that of the memory and the memoryless systems. Okay. So let's see how to check. Step number 1. Find out the output for t is equals to -2, -1, 0, 1 and 2. Okay, find out the output for these time instants. Find out the output for these time instants -2, -1, 0, 1 and 2. Step 2. If for any output, the output depend on the future input. Depend. Okay. If for any output, let me change the statement. So check. What we have to check? We have to check that first of all, if for all the outputs the output depend on the future input only. Okay, if for all the outputs that we have found here, output depend only on the future inputs, okay, then it is anti-causal. If for all the outputs, output does not depend on future input, then it is causal. Okay, we have checked the output. We will see that if we see that the output is not dependent on future, then it is directly causal. And third one is, if it is not satisfying any two conditions, then it is non-causal. Neither this condition nor this condition, then it is non-causal directly. Let's see the examples. For example, yt is equals to x of t plus 5. This is the question. Now here we can see that just put y0, that is x5, y of -1, that is x4, y of -t, x3, y of 1, x6, y2, x7. So we can see that the output is dependent always on future. Y0 is dependent on x5, y-1 is dependent on 4, y-2 on x3, y1 on x6, y2 on x7. So it is always dependent on future inputs. Always depend on the future inputs, right? So it is a anti-causal system. Okay, now the next one, yt is -infinity to t x tau d tau, -infinity to t x tau d tau. Okay, so in this question here we can see that y0 is dependent on -infinity to 0 x tau d tau. So it means that the y0, that is the output at t equal to 0, is dependent on the input from -infinity to 0. The output at t equal to 0 is dependent on the input from -infinity to 0. Similarly, y1 -infinity to 1 x tau d tau. Okay, x tau d tau. Here also we can see that the output is dependent on the past or present. That is, output at t equal to 1 is dependent on the input from -infinity to 1. So it is dependent on the past or present input. Thus here we can see that it will never depend on future. It will never depend on future. So it is a causal system. Okay, it is a causal system. Great. Let's move on. Let's see one more example. Yt is equals to log of xt. Here we can see that the present output will depend only on the present input because the variables are same. So present output is dependent on the present input. So it is a static system. And always remember that the static systems are always causal. Static systems are always causal. Okay, so this is a causal system. Okay, static systems are always causal. Remember this property, this statement. Okay, next example. X of 2t. Let's solve this. So y0 is dependent on x0. Y1 is dependent on x2. Okay. So the present output is dependent on present input. Perfect. The present output is dependent on future input. Y1 is dependent on x2, right? Y of -1 is dependent on x of -2. This means that the present output is dependent on past also. Okay. So this is non-causal because it is neither anti-causal nor causal. This is non-causal. Okay. Why non-causal? The present output at t equals to 0 is dependent on x equals to 0 only. The output at t equal to 1 is dependent on x2, means it is dependent on future. Y of -1 is dependent on x of -2, means it is dependent on past values. Okay, past values. Okay, so now let's move on. So now the linear and non-linear system, the third type of system. What is the method, how to check it? It is very important to understand this, and we have a shortcut for it. Okay, we have a shortcut for it. In maths, we have studied many functions. In maths, we have studied many functions. Okay, for example, log operation, we know the exponential operation, we know the sine function, we know the cosine function. Okay, we know x ki power m. Okay, these are the functions that we know. We know lot of functions, and all of these functions are non-linear functions. Okay, when we draw the figure log x, when we draw the figure exponential to power x, sine x, cosine x, x to power m, where m is not equal to 1, then all these functions are non-linear functions, right? We know that these functions are non-linear functions. These are non-linear functions. Okay, so why I'm telling you this? Why I'm telling you this? This is because if in any equation, any input output relationship, if in any input output relationship, if in any input output relationship, the function on xt is non-linear function, then the system is non-linear. Okay, so if we have any non-linear operation on x, any non-linear operation on x, then the whole system is non-linear. Okay, so this is a very important statement where we can directly see the result. So let's see one examples for it. For example, yt is equals to e to power xt. Yt is equals to mod of xt. Log yt is equals to sine of xt. Yt is equals to 1 upon xt. Okay, so we can see that all these are non-linear because we are having non-linear operation on x. This is non-linear, don't need to check, directly we can say that this is non-linear, non-linear, non-linear operation mod, log of mod, non-linear, sine of x, 1 upon x, x square. All these are non-linear systems because we are doing non-linear operation on the, non-linear operation on the x, that is input. We are doing non-linear operation on the input. Always remember this. Great. But there is one very important rule which can help you a lot, that is this. If we have nonlinear operation on x, then it is nonlinear. If we have nonlinear operation on the x, then it is nonlinear. But if we have nonlinear operation on t variable inside the bracket, then it does not affect the linearity of the system. If we have nonlinear operation on variable t, then it does not affect the linearity of the system. Then it does not affect the linearity of the system. It does not affect the linearity of the system. Okay, it does not affect the linearity of the system. Let's see one examples for it. So suppose we have yt equals to x of log t. So here we can see that so yt is equals to x of log t. Now since here we can see that we have no non-linear operation on x. X is not having any non-linear operation. Rather we are having non-linear operation on t variable. So it will not affect our linearity. This will be a linear system. Now here we are having a nonlinear operation on x. Here we are having nonlinear operation on x. Okay, so it is nonlinear, no doubt about it. Next, yt is equals to log of xt. So here we are having nonlinear operation on x because log is a nonlinear operation, so this is nonlinear. Last is yt is equal to minus infinity to t x tau d tau. Always remember that integration and differentiation are linear operations. Integration and differentiations are linear operations. Okay, so this is a linear operation. This is a linear operation. Okay, now let's see the complete method because many a time for one or two questions we need to know this complete method. First thing. Second thing, in many theoretical statements they can ask you these complete methods because the definition is very important. Let's see the definition. The definition says that any system that follows superposition are called any system that follows the superposition are called the linear system. So let me tell you what is a superposition theorem. Superposition theorem has two parts, that is homogeneity and additivity. This is important from the theoretical point of view that might help you in some exams. Okay, so superposition has two parts, that is homogeneity and additivity. Superposition has two parts. Additivity and homogeneity. Okay, so let's see what is the meaning of this. So the superposition says that if we have a linear system, if we have a linear system, and for input x1 it produces output y1, for input x1 it produces output y1, for input x2 it produces output y2. Okay, then additivity says that, okay, just I'm repeating the statement. So if we have a linear system, for input x1 it is producing output y1, for input x2 it is producing output y2. Okay, and if we have if we see that the additivity says that if we apply x1 plus x2 as the input, if we apply x1 plus x2 as the input, if we add the two inputs, then the output should be y1 plus y2. This is given by additivity theorem. This is given by additivity theorem. So additivity theorem says that if we add the two inputs, then the output will also get added. This is additivity. And what is homogeneity? Homogeneity says that if we multiply the input by some constant a, then the output will also get multiplied by that constant. So this is given by homogeneity. So what is additivity? Additivity means if we add the two inputs, we should get the result, that is addition of two outputs. If you multiply the input by some constant, output should also get multiplied by the same constant. So this is the additivity and homogeneity. Combining the two, we get superposition. Superposition theorem says that that is a times of x1 plus b times of x2 should produce the output, that is a times of y1 plus b times of y2. Okay, a times of x1 plus b times of x2 gives the result, that is a times of y1 plus b times of y2. Okay, so there are two examples for making this clear, that how it actually works, how to check using superposition theorem. So this is the input output relationship of a system. Let us first of all write this equation in terms of a statement, that is what the system is actually doing. We should know what the system is actually doing. What is it doing? We can say that the output is equal to input. Output is equal to a times the input plus B. Output equals to A times of input plus B. Now, let's see the steps. So, if we give x1 as the input, the output will be A times of input plus B. So, output will be A times of x1 plus B. Okay. Now, if we give the input that is x2, if we give the input that is x2, then the result will be A times of input plus B. Now, checking the superposition theorem, we give the input that is alpha times x1 plus beta times x2. Okay. So, this is the input that we give, alpha times x1 plus beta times x2. We will get the output that is A times of the input, A times the input plus B. Okay. A times of the input plus B. This is the output that we will get. Now, this is very important to observe that this output, if the system follows superposition, then this output should be equal to alpha times y1 plus beta times y2. This is your y1 and this is your y2. So, the output should be alpha times y1 plus beta times y2, but here we can see that the output is not equal to this, because alpha times y1 plus alpha times beta times y2 will be plus okay. So, we can see that this output is not equal to this. Okay, this output is not equal to alpha times y1 plus beta times y2. So, the system is non-linear. So, always remember that when we add anything extra in the equation, then it will become non-linear. That is, yt is equals to 3xt plus 5. Yt is equals to 2xt plus cos t. Yt is equals to 2xt plus sin t. These all are non-linear. Okay, these all are non-linear. But if we multiply anything with xt, this will remain linear. Suppose we have yt is equals to cos t into xt. Suppose we have yt is equals to cos t into xt. So, this system will be linear. This will be a linear system. Okay, this will be a linear system. This is non-linear. This is non-linear. This is non-linear, but this is linear. So, how to remember? Always remember these two, 3 points for linear systems. First point is, any non-linear operation on x will make it non-linear. Any non-linear operation on t variable, it will not affect the linearity. Okay, it will not affect the linearity. Second, integration and differentiation are linear operations. Next is superposition theorem. You don't need to remember this superposition theorem. You just have to remember that if anything extra is getting added, then it makes the system non-linear. But if anything is getting multiplied only, it is not getting added, then it remains the linear system. Okay. Last one is this conjugation is also a non-linear operation. Conjugate is also non-linear operation. Conjugate is also a non-linear operation. Always remember that. Let's see how to find it out. So, suppose x1 is the input, then x1 conjugate is the output, x2 is the input, x2 conjugate is the output. If we give alpha x1 plus beta x2 as the input, then the output will be, output is simply conjugate of the input. If this is the input, then the output will be alpha times x1 whole conjugate. Okay, whole conjugate. So if we solve this, we'll get alpha conjugate x1 conjugate, beta conjugate x2 conjugate, and this is not equal to alpha y1 plus beta y2, alpha y1 plus beta y2. This is not equal to alpha y1 plus beta y2. Okay, so this is a non-linear system. So you just have to remember these 2-3 points, okay, that I have already told you. Just add that conjugation is also non-linear operation. So here we can see that there is 1 by t time 1 by xt times 1 by xt term. So here we can see that it is x of t square plus xt inverse. So this term makes the system non-linear. Okay. If we add anything extra cos t, so it makes the system non-linear. So this is also non-linear. Okay. Next, xt plus 4 times of x of t minus 4. Now this term is not an extra term because this is the input only. Just it is getting shifted. So here we can see that this is a linear. We have no non-linear operation on x. This is also linear. So overall system is linear. Overall system is linear. Okay. This one. Here we can see that this is linear operation. This is linear operation, but we have an extra term getting added. So this makes the system non-linear. Okay. This makes the system non-linear. Now let's move on to the next, that is time variant and time invariant systems. So now let's continue with the time variant and time invariant system. So time variant and time invariant systems are how to check. Let us see. There are only three points that will make you very much clear that how to find out that the system is time variant or time invariant. These 3 points are very simple and you will be able to solve any problem using these 3 points. Okay, using these 3 points you can solve any problem very easily. So there are 3 points or 3-point shortcut. 3-point shortcut. What are these? What are these? The first point is if in the expression of input output, if in the expression of input output we have the variable t is not there. Okay. Okay. So we see some changes in variable t. In variable t. Okay. Then the system is time variable. Then the system is time varying. Okay. Then the system is time varying. Second, if in the relationship, if in the relationship, the if in the relationship there is addition of any time dependent term, there is addition of time dependent term other than input. Other than input. There is addition or multiplication. Okay, just add one more point. Addition or multiplication. Addition or multiplication multiplication of any time dependent term other than the input, then the system is time varying. Okay, this is the second point. We'll see all these points with the help of example. And the third is, if we have a time dependent relationship, time dependent relationship means, suppose this kind of relationship, that the relationship is xt plus 1 for t greater than 0, and it is xt minus 1 for t less than 0. So this is time dependent relationship, means the relationship changes with time. For t greater than 0, this is the relation. For t less than 0, this is the relationship. These kind of systems are always time variable. So we have seen three time variable points that when the system can become time variable. First is if we have made any changes in the variable t. We'll see the examples. Second is if we have any time dependent term getting multiplied or added in the system, then the system will be time varying. Third is if we have time dependent relationship, then also the system is time varying. Okay. So now let's see examples. So here yt is equal to x log t. Here we can see that we have made changes in the time variable. Here variable is not t, rather the variable is log t. Means the variable is getting logged. Okay. Here we are doing log operation on variable t. So we have made changes in variable t. Changes in the variable, so it is time varying. Here we can see that yt is equals to sine of xt. Here we have made no change or no manipulations in variable t. Here variable t is intact. Here we have variable inside the bracket, we have only variable t. So variable t is intact here. So it is time invariant system. Okay. Next is yt equals to log of xt. Here also we can see that the variable t is intact. Here variable t is intact. So this is time invariant system. Here we can see that in the integration in the RHS, we have variable t which is intact. Okay, so this is time invariant system. Variable t is intact. Okay, next let's see the examples. So here we can see that variable is t. Here also we have variable t only. We have not done any manipulation in variable t, only we have added 4. But variable t is intact. Okay, there is no issues in it. So it is time invariant system. Next, here we have time dependent term getting multiplied with xt. So it is time variant. Okay, next. Here we have the time dependent relationship. For t greater than 1, this is the relationship. For t less than 1, this is the relationship. So this system is also time variant. Issues in it. Let's see more examples for more clarity. Because these 3 points, you will be always able to solve any problem of time variant, time invariant. X of minus Okay, so let's see all the examples. First one, we have manipulated the variable t by minus t. Okay, we have multiplied variable t by minus t. So this is time varying. Okay, here in the next problem, we have changed the variable t by 2t. We have multiplied the variable t by 2. So this is also time varying. Okay, we have changed the variable to t square. This is also time varying. We have added a time dependent term. So this is also time varying. But in this last example, the variable t is intact. So this is time invariant. Okay. So always remember that if the variable is t plus 4, then it is not called manipulated. Okay. Because variable t is intact. Okay. We have just added 4. Similarly, if we have t minus 4, so this is also not called manipulation. These two are not called manipulation. Okay. Just an example. Suppose this is the question. So here the variable t are intact. We have not done anything with variable t. So this is time invariant. But what about this? X of 2t. So x of 2t, we can see that here we have changed the variable t to 2t. We have multiplied the variable with 2. So this is time variable by time variant system. Okay. So any kind of problem you can do with this these three steps. Okay. I don't think you will find any problem not able to solve with these three very simple steps. Okay. So more examples. Okay. So here also we can see that the minus t is there, minus t is there. So we have changed the time varying time variable, that is minus t. We have made it minus t. So this is time variant system. Okay. So here we can see that variable t in the RHS is intact. Variable t, variable t. Only we have added 4 or subtracted 4. So this is time invariant system. Okay. So like this you can solve all kind of time variant and time invariant systems very easily. Okay. So now let's move on to the last two the systems, type of system, that is stable, unstable, and invertible, non-invertible systems. Okay. So let's continue. So now let's come on to the stable and unstable systems. For stable and unstable systems, first of all, we have to study the bounded signals. First of all, we have to study what is a bounded signal. Okay. So bounded signals. Bounded signals are those which are bounded on amplitude axis. Okay. Here the bounded means we are talking about the amplitude axis, it is bounded. So the signals which are bounded with respect to the amplitude axis, they are called bounded signals. Or we can say that the signals which have finite amplitude, or the signals which have finite amplitude at any time instant. Bounded signals are signals which have bounded which have bounded which have finite amplitude at any time instant. Okay, which have finite amplitude at any time instant are called bounded signals. Okay, and any system is called stable. Any system is called stable any system is called stable if if for bounded input we get the bounded output. Okay, so these two are very important things. First is bounded signals. Bounded signals are those which are bounded on the amplitude axis, matlab they have finite amplitude at any time instant. Second is any system is called stable if it is bounded, if for the bounded input we get the bounded output. Okay, so we have written here what is a bounded signal. So bounded signal I have already told you, signal which has finite amplitude at any time instant. Finite amplitude at any time instant. Finite amplitude at any time instant is called the bounded signal. Okay, and I've already told you what is Bibo stability. Bibo stability means bounded input, bounded output stability. Bounded input, bounded output stability. Okay, that is for bounded input we should get the bounded output. Okay, this is the meaning of it. Okay, now how to check? What is the method to check? What is the method to check? We'll solve examples also. We'll solve examples also, but let me tell you the method. So what is the method? The method is apply ut as input. Apply ut as input to the system. Okay, ut is a bounded signal because it has always amplitude either 1 or 0. Either the amplitude of this signal is 1 or 0. So apply ut as input to the system. If the output is bounded, means output amplitude is also finite always, then the system is Bibo. Then the system is Bibo system. Bibo system means the system is stable system. The system is stable system, else it is not. This is point number 1. Second point is many a times ut fails to give the result. So sometimes we also need to check by applying the input sine omega naught t or cos omega naught t also. But for 95% of the cases this is valid. For few cases there was one PYQ, for that we need sine omega naught t or cos omega naught t, because these two are also the bounded inputs. Okay, these two are also bounded inputs because the value or the amplitude is always from -1 to 1. So these are also bounded. So when the input is sine omega naught t or cos omega naught t, the output should be bounded. Then the system is stable. So only these three are more than sufficient for checking ut, sine omega naught t and cos omega naught t. Okay. So let's see few examples. Let's see few examples. Yt is equals to x of t minus 1. Yt is equals to x of 2t plus 3. Yt is equals to txt. Yt is equals to log of xt. Yt is equals to sine of xt. Suppose these two are the examples. So let's solve these. The first example is we are only shifting the input. So if the input is of finite amplitude, if the input is of finite amplitude and we are just shifting it, so the result will also be bounded. So if the input is bounded input means the amplitude is always finite. So the output will also have the finite output always. Okay, so this is Bibo system, means it's a stable system. In the second one also we are only doing scaling and shifting. So if the input is of bounded category or the amplitude of the input is always finite, then output will also be finite. That is, output will also be Bibo. Third is TUT. TUT means we are multiplying the input with T. Now, just take an example here. If the input is UT, the output will be TUT. That is, input is UT, the output will be ramp. Ramp means it will go to infinity as T tends to infinity. So, output is not bounded. So, this is not BIBO. Even if the input is bounded, that is, input is UT, the output is TUT. TUT means the output will go to infinity as T tends to infinity. Last is log of xt. Log of xt, we know that even if the input is bounded, for example, input value is 0, then log 0 will go to minus infinity. The output will be unbounded. Output will be not bounded. Even if the input is bounded, the output will be not bounded because log 0 is minus infinity. So this is also not BIBO. Okay, last. Sine of xt, yt equals to sine of xt. So many a times you don't need to put ut, sine omega t or cos omega t. By understanding also you can solve these questions. So yt equals to sine of xt. Now xt can have any value, but sine of xt will have only value minus 1 to 1. So output will always be bounded only. Output yt will always be bounded. So input is bounded, output will always be bounded because sine of xt will always give the value minus 1 to 1 only. Next, for example, yt equals to xt plus 5. So you are simply adding 5 to a input. So if input is bounded, input has finite value, finite amplitude, you are simply adding 5 to it. So obviously the output will always be bounded, stable. Yt equals to txt is unstable because we know that, for example, if input is ut, the output will be TUT, that is ramp, and thus ramp goes to infinity, the output is unbounded. Okay, xt upon t. Here we can see that at t equals to 0, yt value will have infinity, yt will have infinite value. Thus, the value of the yt will be infinity, it will go to infinity. So, this is unstable. Yt equals to sin t into xt. So, this is finite value always. This is also always finite. So, finite into finite will always be finite because input is bounded. This is always from minus 1 to 1. So, yt will always be bounded. So, this is stable. This we have already done. This we have already done. Now, let's see one or two examples. Suppose this is a signal minus infinity to t x tau d tau. Okay. Now, in this case, if we want to find out yt at any time instant, for example, we want to find y0. So, y0 will be minus infinity to 0 x tau d tau. Now, since input is finite, input is having a finite value, but we are integrating it from minus infinity to 0. We are integrating the input for a infinite duration. We are integrating the input for a infinite duration. Thus, y0 may go to infinity. I am repeating the statement. If input is a finite amplitude, if input is having a finite amplitude, for example, this is the input, let us say. Now, if we integrate the input from minus infinity to 0, so we are actually finding the area of this plot from minus infinity to 0. So we are integrating for an infinite duration, we are integrating a finite value for an infinite duration, the value may go to infinity. So this will become infinity and thus this system will be unstable. This system will be unstable, okay? One more example on this. Suppose yt is equal to minus infinity to 2t x tau d tau. The same explanation for this. This is also unstable system, or this is not BIBO stable, not BIBO system. Suppose we have this t minus 5 to t x tau d tau. Now, if you put any condition here, for example, y0. So y0 means we are integrating from minus 5 to 0 x tau d tau. So here we are integrating for only a limited duration. We are integrating from minus 5 to 0 only. For a limited duration, we are integrating a bounded signal. So always the output will be bounded. For example, y of 1000 will be, we will be integrating the signal from 995 to 1000. So we can see that we are always integrating over a finite duration, that is 5. Okay, we are integrating over a finite duration. So this will always be stable. The output will always be finite. The value will always be finite. So this is a stable system. This is a stable system. Okay. One more example. Suppose yt is equal to minus infinity to t x tau cos t cos tau d tau cos tau d tau. So here we can see that if we put input cos tau, if we put the input cos tau just for checking, since cos tau is bounded, so if we put xt is equals to cos t, so we'll put here cos tau minus infinity to t cos square tau d tau. Okay. So here we can see that since we are integrating from minus infinity to t cos square tau d tau, cos square will become positive, and we are integrating from minus infinity to minus infinity to t cos square tau d tau, cos square will become positive, and thus this will become unstable system, because this value will always be infinity. So input is bounded but output is unbounded, so the system is unstable. Okay, I hope this is clear to all of you. Now let's move on to invertible and non-invertible system. Many a times invertible and non-invertible are not included in the GATE syllabus. Moreover, this is not important because GATE have not asked questions on invertibility and non-invertibility. Just one statement that LTI systems are always invertible, that is very important. Okay, LTI systems are invertible. Now what is invertible system? Invertible system means, let me define it for you. Any system is invertible any system is invertible when any system is called invertible when we can get back the input from the output. Okay, we can get back the input from the output. So any system is invertible when we can get back the input from the output. So if we have any system, suppose we have a system, where input is xt and output is yt. So this system will be invertible if we can get back the input signal xt from yt. If we are able to get back xt from yt, if we can extract xt from yt, okay, the system is called invertible if we can extract xt from yt. Now, what is the method to check? There are only very simple properties or very simple method. What is the method to check? The method to check is very simple. That is yt must have complete information Yt must have complete information of xt, means the output should have complete information, complete values, complete information about xt. Okay. Second, no many to one mapping from input to output. No many to one mapping from input to output. For example, yt is equal to xt square, x square t, or yt is equal to mod of xt. So why these are non-invertible? Why these are non-invertible? Because if the input is -5, the output will be 25. The input is 5, then also the output is 25. Thus, when we have two values of input for which the output is 25. So if we have the output value 25, we cannot figure out that the input was 5 or -5. Same is the case in this one also. If the input is -5, output will be 5. If the input is 5, the output is 5. So here also, if the output value is 5, we cannot get back what is the input, 5 or -5. So these systems are not invertible. Okay. So only two things you have to check. There should be no information loss. Second is LTI systems are always invertible. And the third is many to one mapping should not be there from input to output. So let's see the examples. Suppose yt is equals to 2xt, we are simply multiplying the input by 2. So we can get back the input by simply dividing the output by 2. Okay. So this is invertible. This is invertible. Second one. Here we can see that y0 is equal to 0 always. So x0 is lost. We can see that x0 is lost. We can see that x0 is lost. We have lost x0. So since x0 is lost, so information is lost. So here we have information loss. And since there is information loss, so non-invertible. Non-invertible. Third is integration. Integration is invertible because it's we can differentiate and we can get the answer. So it is invertible. But differentiation is not invertible because when we differentiate a signal, we get rid of the constant term. Okay, constant term is removed. And since the constant term is removed, thus we cannot get back the constant term. For example, if we apply DC signal here, so differentiation of the DC signal will be 0 and we cannot get back the DC signal again. So differentiation is not invertible. Yeah, always remember that. This is not invertible. Next is contracting the signal. In continuous time domain, we have already seen that when we contract any signal, there is no information loss. When we contract a signal, there is no information loss. So this is invertible. When we expand a signal, there also there is no information loss. But in discrete case, when we compress, when we contract, when we decimate, then there is an information loss, and thus this is non-invertible. This is non-invertible. But in the last case, when we are interpolating, when we are padding zeros, there is no information loss. So this process is invertible. The last one is invertible. Okay, the last one is invertible. So these are the things that we have to cover, the type of systems. We have covered all the type of systems, right? So I hope these systems are clear to all of you. So thank you, dear students, and now we'll start the LTI systems in the next session. Thank you. Bye-bye.